Hello, everyone. My name is Vladimir Gurevich. I'm a principal engineer at Intel and a director of Intel Connectivity Education Hub.
Hi, everyone. I'm Andy Fingerhut, also a principal engineer at Intel and also the co-chair of the P4 Architecture Working Group. So, Vlad, what do you want to talk about today?
Well, I think many of our viewers are already familiar with the basics of P416 language and with the open source behavioral model known as BMV2. If not, they can find plenty of materials right here on p4.org YouTube channel and watch those. And I'm sure that they also know that aside from the behavioral model, which certainly is a great tool to familiarize yourself with the language and get started there, are real hardware implementations. And that's what people use to build real networking devices like switches, routers, load balancers, and many, many others. These devices are a lot faster. They come with high-speed network interfaces, but also are much more complex to use.
That's my introduction to say, how fast is it?
Well, Intel Tofino that I wanted to discuss today is probably one of the most well-known devices, and it is capable of switching 4.88 billion packets per second, or 6.5 terabits per second. That's about several orders of magnitude more compared to the fastest software-based implementations like DPDK.
Yeah, and Intel, in following along with common switch ASIC style of keeping up with the latest ASIC technology, will be doubling that bandwidth up to 12.9 terabits per second.
That's right. Tofino 2 is twice as fast, and there are many other notable enhancements. Today, we probably won't have time to go into them, but if people are interested, there's definitely lots of information on the Intel side.
So about 1.2 gigahertz clock, that's way less than the packet per second rate. So how do we do that?
Well, before I answer this question, first of all, I want to point our viewers to the talk Programmable Devices and Programmable Data Planes at Terabit Speeds, which provides a great introduction to both devices. And to answer your question about the performance, the main secret is parallelization. That means that every clock, Tofino performs a lot more work compared to a traditional CPU. First of all, if we look at the high-end Tofino diagram, we can see that the device contains 4 so-called processing pipes.
So, which we can think of like in a traditional multi-core CPU, each of those is like one of the CPU cores.
Very much so. In fact, some devices have 4 such pipes, others have less, for example, 2 if we're talking about less expensive models. So
that total clock packet rate, about 4.88 billion packets per second, that's 4 times the 1.2, but that's just starting a packet. You have to finish it too, right?
Yes, this particular arrangement does not explain the performance difference. So what is really important is what happens inside. And so here I wanted to show how the packets are processed inside each of these 4 processing pipes from the beginning to end. First, the ingress packets are received by the corresponding ports MAX. These ports are hardwired to a processing pipe, and each pipe can process packets from up to 1800 gigabit per second ports. 16 of them are standard Ethernet ports, and there are 2 extra ones for circulation, packet generators, CPU interfaces, and so on. And these 100 gigabit per second ports can also be split into individual 25 gigabit per second ports, and there are many other combinations. That's not that important. What is interesting, and that's when we start talking about parallelization, let's see what happens once these packets are received. Once they're received, they are first parsed by the programmable parsers, and we can see that we have 18 of those. So that each of this 100 gigabit per second port can get its own dedicated parser.
Makes sense. So yeah, every one of these is operating in parallel, the parsers as well as the 4 pipes.
Right. And also parsing is a relatively slow process because if you think about that, it's a finite state machine. That's how parsers are represented in P4 language as well. That might require multiple state transitions and therefore multiple clock cycles to perform parsing. Also, we need to remember that it simply takes time, even at 100 gigabits per second, to simply receive the data from the wire in the first place. So therefore, it makes a lot of sense to have multiple parsers working in parallel and feeding the single match action pipeline that processes one packet per clock.
So how does all this data get in there then?
Well, the data is passed from the parser into the match action pipeline and then throughout all its stages and all the way to the deparser using a programmable header and metadata bus, also known as PHV, which stands for packet header vector. And there lies another qualitative difference. This bus is 4 kilobits wide.
So yeah, if you were to have a 64-bit processor, that's a lot of 64-bit general purpose registers to make that up.
Oh yeah. Oh yeah. And I don't think it will be really a big stretch to call Tofino 4 kilobit processing unit, and Tofino 2 is even more capable in that sense.
So then the packet goes down the match action pipeline after that?
Yes, and in case of Tofino, the match action pipeline consists of 12 stages, which are also called match action units or MAUs. In case of Tofino, that's 20 stages, but here's what's really important. First of all, in each stage, we can perform multiple lookups in parallel, up to 16, in fact, meaning that you can find more than one P4 table inside each stage.
So I've spent a lot of time reading the P4 spec and editing it, and there's several sections in there where it describes all the behavior as sequential execution.
That's right. That's precisely what the P4 spec says, but it doesn't mandate that any particular P4 implementation must execute code sequentially. It only needs to ensure that the effects of the code execution will be the same as if the code was executed sequentially. In reality, though, most of the P4 programs exhibit a lot of parallelism, and P4 compiler for Tofino is really good at noticing and exploiting this parallelism.
So much like C compilers are allowed to take advantage of parallelism in code if they can find it, as well as modern processors. But any examples for P4 in particular?
Precisely. And if we are looking at the typical data plane code, it actually exhibits a lot more parallelism than many C programs because most network headers consist of individual, usually independent fields, and therefore most of the operations are parallelized. For example, if you form a network header and it has 10 or 20 fields and you need to fill them up, the order wouldn't matter, would it?
Yeah, I mean, I think that's one of the key observations that the P4 language designers noticed is that a lot of packet processing really has a lot of parallelism to it that a lot of C programs don't.
In case of Tofino, each stage can perform up to 224 elementary operations, such as assignments and simple additions and subtractions and logical operations, etc., in parallel. And it can also perform more complex operations, although probably not in that amount. So if you think about every clock, every MAU can perform 224 operations in parallel or up to that number. And obviously we have 12 MAUs. So that's quite a lot.
Yeah, I mean, I guess if I were to compare it to, let's say, modern x86 architectures, they have a lot of vector operations, but I've not seen any that go up to that many operations per clock cycle.
Yeah, and that's pretty much this high parallelism, even though we don't say that Tofino is a massively parallel device, maybe that will be a slight mischaracterization, but overall, that's precisely what we're looking at. So once we finish this match action processing, the packet headers are assembled in another device called deparser, and then they meet the actual payload of the packet that is not processed in P4 programs, as we know, inside the ingress packet constructor. And then the reassembled byte stream goes into the traffic manager, where it is buffered, potentially replicated if there is a need to do multicast, queued, and eventually scheduled to go to the egress process. And at the egress, there is another set of separate parsers, one for each of the 100 gigabit egress port. So actually, we have 36 independent parsers within one processing pipe. And that means even more processing in parallel. And that's what's interesting, is that the packet will go through the same set of match action units.
And I see, yeah, you've got the color coding for the ingress and egress kind of mingled in there in the MAU stages. And if I had to do all that arranging of things by hand, that would be pretty tedious, but thankfully the P4 compiler can do that for us.
Yes, that's something our users do not have to worry about, which resources within each stage have to be assigned to ingress or to egress processing. All this is done by the compiler automatically. The compiler analyzes the code and allocates the resources accordingly. After the egress match action processing is finished, and again, just to repeat myself, we will be going through the same stages, but use different resources, in this case, light blue. And what it allows us to do, it allows us to very flexibly divide resources depending on whether the program is ingress or egress heavy. So once the packet finishes this processing, it goes into the egress deparser, meets its body inside the egress packet constructor, and then is sent out using our packet maps.
And Tofino definitely has a couple of other options for, let's say you have a case where parsing was particularly tricky, or ingress processing, you want another go at it, you can resubmit the packet back from end of ingress back to the beginning. And another is, if for some reason you want to reduce latency and happen not to need any egress processing after the traffic manager, you can just completely skip over it.
Yes, Tofino allows all these possibilities, and it definitely allows us to create either more complex programs for more complex cases, or to have a much lower latency if the processing is not very difficult to do. So for the dessert, I just wanted to show our viewers a simple animation. And this animation will show how the packets go through the processing pipeline.
And so, yeah, so like other multi-core processors, not only is there parallelization in the multiple pipes, but we have pipeline parallelization here. So the pipeline depths here are actually quite a bit bigger than most processors here in Tofino, right?
Yes. Aside from the fact that this is essentially like a dual-threaded processing unit, we can see that the number of packets that are processed, even in the simple animation, is quite high, even though it's one packet per clock. So in the real device, we're talking about several hundred packets processed in parallel, because that is the that's how many packets the pipe can process at the same time. The actual number depends on the complexity of the program as well. So the more complex the program, the longer is the pipeline, and therefore the more packets it can process in parallel. The simpler the program, the shorter this processing time will be. But overall, several hundred packets per clock, and then you multiply it by 4 pipes, and we're talking about probably about 2,000 packets that are processed inside Tofino at the same time. So that's way more than the number of, say, cores that you have even in some monster CPUs of the modern times.
Yeah, definitely. No, I mean, that's what you need to compete with the best you can do in silicon for packet processing. So good architecture. And so I think we've talked quite a bit about some good introduction to Tofino hardware architecture here. And I have actually taken, Vlad teaches a course at the Intel Connectivity Academy that I've taken, gosh, it's a year and a half now, ago now, but I would heartily recommend it as a way to learn not only these things, but a lot of other tips and techniques for programming Tofino for these and a lot of other features.
Well, Andy, thanks for the plug. Definitely appreciate that. I guess we should now talk about how these devices look from the P4 standpoint. So you've been involved with several P416 architectures from anywhere from V1 model to PSA and now PNA, portable network NIC architecture.
Yeah.
What about Tofino?
So Tofino has its Tofino native architecture, which has a lot of similarities to the portable switch architecture. But I mean, in some ways, the portable switch architecture is in some ways, it's a lowest common denominator architecture. It's the things you expect to find in any switch ASIC. But Tofino definitely has its own special features that are above the lowest common denominator. So we wanted to expose all of those in the Tofino native architecture.
It's no secret that vendors tend to keep a lot of the information about the high-speed devices under the wraps. It's understandable. But we at Intel believe that opening such technical information is crucial to the industry. As a result, we committed to gradually open Tofino technical information and created a special GitHub repository called Open Tofino, and the link is right here and also will be down in the description of this video, where we now publish such information. We started by openly publishing all the interfaces provided by Tofino native architecture, thereby allowing everyone to publish their P4 code written for Tofino. Later on, we followed up by publishing all the interfaces provided by Barefoot Runtime Interface, making it possible to openly publish control plane code written using Intel P4 Studio APIs. And now we've already published a comprehensive document that describes the Tofino native architecture in great detail and what's really important in plain English. And here I would especially like to thank Andy, who is the main force behind this important document and who made it a reality through very hard work.
I thank you. I have to give credit to the authors that started the document and laid down the framework for it and a lot of the text, and which I definitely did a lot of writing and editing on. But thanks also to Vlad for his tireless, I will say tireless reviewing and suggestions for improvements on the document as well.
Okay, so let's get to the chase. We saw the diagrams of V1 model architecture, PSA and TNA, and especially the last two look very similar. I'll just flash them real quick so that people can try to catch the differences. Is that correct?
Yeah, they are very similar. And but yeah, we want to talk about the differences here today and focus well, some of the commonalities, but focus on some differences here. So like any P4 architecture for P416 and most switch architectures, we see that, you know, like PSA, TNA has packets coming in on the left side here from network ports, going through an ingress parser, control, and deparser, then a traffic manager that can do packet replication or mirroring, and then we have egress, similarly, parser, control, and deparser. Now, unlike PSA, so one of the things that distinguishes architectures, besides which programmable blocks there are, is what data passes between these blocks, these programmable blocks. And so the PSA defines its standard metadata, term of art they use in the spec there, but in TNA we just call it intrinsic metadata. Same idea, but the fields that we have in TNA have some things in common. So for example, you'll find an ingress port for packets coming in off the wire. You obviously need that, an ingress timestamp. That TNA shares that with PSA as well, but there's a lot of metadata fields that are unique to TNA. And so we see the names of all of these structures abbreviated down here at the bottom, the ingress intrinsic metadata at the left, working on to the right, and they are passed down the pipeline. Now, while a lot of diagrams will show these arrows of ingress intrinsic metadata out of the ingress parser into the control as a connected line, we've shown them here as separate arrows simply because it is possible, and in some cases TNA takes advantage of this, for the architecture to modify some of these intrinsic metadata fields before they get passed to the next control block.
And I guess the other important difference, of course, are TNA specific externs that we'll be discussing a little bit later.
Right. Yep. There's several examples of those. Yep.
But the idea, I think, is the same. And the way people should think, I guess, about programming in P4 is really filling out these programmable components one by one and making sure that's coherent and forms the final data plane algorithm that they would like to express. So therefore, the template for a TNA program looks pretty much the same as anything else. The main difference, of course, is that aside from the file core.p4, we need to include the file tna.p4, which contains all the definitions of TNA objects. And then we have to write essentially 10 different components, 5 for each of the pipelines. That would be the definitions of the structs which carry our headers and metadata in ingress and in egress. And then we have to define the algorithms for our ingress and egress parser, ingress and egress match action, or sometimes people say match action pipeline, sometimes they say match action control, and ingress and egress deparser. And then what we need to do, we need to take these last 6 ones, actually, the ones that I have in blue, and create packages, assemble them essentially so that we can form a full P4 program.
So this is precisely where one place where TNA differs from the PSA architecture and provides additional capabilities, because first we create this so-called pipeline package instantiation, and it contains our ingress and our egress parsers and deparsers and controls.
Which is precisely what the Tofino processing pipe is.
And so that's why we call that that's why we named the instance here pipe, and then we use that further down below at the bottom for the top level instantiation.
So why do we need such complexity?
So for a lot of programs, you don't. If you wanted to use a 4-pipe Tofino and you want every single pipeline to process packets exactly the same way as each other, which is a pretty common case, this is enough. But if you ever want to take advantage of the hardware capabilities that TNA provides, where we could load compile and load different P4 code into different pipes, then we need some additional flexibility here.
Okay, so if we take a look at the program code, how different it is compared to, say, PSA?
So a lot of it is very similar. You find instantiations of and definitions of parsers, controls, and deparsers. One main difference is that the definition of these structures, the intrinsic metadata structures, you'll find a lot of different fields that we'll see later that is in each one of these. And the number of them is also larger because we've broken it down into smaller specialized structures depending upon the source and destination of the data, whether it originates in the ingress parser and goes to the control or so on, a few other cases like that.
Okay, should we take a look deeper and see what those structures are?
Definitely, that's where all the fun is.
Okay.
So here we see we start off with the intrinsic metadata that comes in to the ingress parser. And so ingress port is familiar from PSA. The ingress MAC timestamp here is, PSA has this, but in the PSA, it doesn't define the units or basically just leaves it open to each implementation. So here in TNA, we have specifically nanosecond units. So even though the clock doesn't run at exactly 1 gigahertz, these timestamps do advance at 1 per nanosecond. And we have one for the MAC timestamp when the packet arrives, the first byte of the packet arrives to the MAC. And then we have another one, which is just after the ingress parser, the global T stamp. So which represents, the difference of those represents the amount of time that the packet took to finish its parsing. And I'll just mention briefly as a note ahead, we have another timestamp when the packet reaches the egress. And so all of these timestamps are in the same units and they're all in a single device, they're all synchronized with each other. So you can use differences between egress and ingress timestamps, for example, to get a very good approximation of the queuing latency of the device for your particular packet. And so you're guaranteed that all of these timestamps are going to be synchronized within one Tofino. And then we have options that you can enable to synchronize them between multiple Tofino devices as well, using IEEE 1588. Another thing we have here is the parser error. So this is a little bit different than the standard, the P416 language standard. Here, though, we've broken down the actual parser errors that the Tofino hardware can actually detect and see. And these are all documented in the TNA in more detail. We won't go through them here, but just so you know that they are different than the P416 language standard, but are very specific, very detailed reasons exactly why the Tofino parser can give errors.
Okay, so what about the outputs that the ingress control can produce?
Yeah, so we definitely have some enhancements over what you'll find in PSA here as well. So you'll notice, for example, there's a drop control field in the ingress intrinsic metadata for the deparser. That's output from the ingress control. And you might be wondering, well, why is that 3 bits wide? And it turns out that Tofino has an ability to have independent drop control for, let's say, the regular copy of the packet, unicast or multicast, versus a copy to CPU, copy of the packet, that you can independently disable those copies. Another difference you'll see is, well, it won't be so obvious from looking at this metadata field, but if you read the TNA spec, you'll see that there's a ucast egress port and there's multicast control and copy to CPU. And if you read the TNA spec, you'll see that you can have the same packet do all 3 of those things from the same original packet just by assigning appropriate values to each of these fields.
Even 4, in fact, because there are 2 multicast groups, one to multicast packets, say, in the underlay network, and the other one to multicast in the overlay network, in case people really want to implement some tunneling protocols.
Yeah, tunneling protocols, or sometimes layer 2 and layer 3 multicast, that can be also very useful to separate those out in the control plane and the data plane. And then other things you'll notice here are we have fields labeled with the cut through in the name. So Tofino implements, like many switch ASICs, the ability to do cut through forwarding to reduce latency, where you can start processing the packet in egress before even the last bit of the packet has arrived on the input port. And so we have controls here that in your P4 code, you can specifically enable or disable this cut through feature on a per packet basis. And then one more interesting one, the deflect on drop is a useful feature if you want to get better. It's a good way in Tofino that you can say, well, if my packet is going to be dropped because of congestion, I'd like to be able to mirror a copy of that or send a deflected copy of that packet to a different output port, perhaps some monitoring station or even a tunnel perhaps, so that you can get a lot more detail on which packets are being dropped and when. It's
definitely a very useful feature because you never want any packets to disappear just mysteriously in some black hole. So very, very useful for debug and that kind of stuff. And I think what's really important is that one can use this intrinsic metadata very creatively and write quite unique actions that manipulate one or more of these intrinsic metadata fields in some creative ways and achieve a lot of effects that maybe the designers didn't really thought of, or they didn't have to implement a special feature for that. That's the whole power of P4, that we can compile simple things to achieve some great results. So for example, here we can show an action called quicksend. And what we do here, we send the packet to a particular egress port, and at the same time, we direct it to a particular queue. And also we asking the packet to bypass the egress pipeline. So nothing special, just setting a couple of different things inside this intrinsic metadata, and we have a totally new effect.
Yeah, and here we have an example of Igmp Snoop. So this is, we're going to be sending out a multicast copy of the packet by assigning the multicast group A field, but also sending one to the local CPU, because that's the Snoop part of it, that we want the control plane to see a copy of this as well. And then in this example, we're enabling the multicast cut through for this copy as well.
Or here, for example, we have a special drop, much stronger drop action that you would normally want. maybe, but we're trying to get rid of multiple different types of packet copies from the system, and we use P4 exit statement so that no other processing can occur. So if down inside of a program we have, say, code to increment counters or execute meters, none of that will happen. That's a very useful feature. And I think what is also important that we can, because this is just metadata, we can always change our decisions. So for example, we can try to mark the packet for drop, but then if we don't like that, we can set drop control to 0 and resurrect the packet, obviously. That only happens if we didn't use the exit statement beforehand.
Yeah, resurrect can't save you from exit. Exit is exit. All right, and now my favorite part of the intrinsic metadata, the stuff we get out of the traffic manager, which gives us so many statistics, and it's up to your imagination how we get to use them. But first, I'll start with picking through this. The NQ queue depth and the DQ queue depth are the length of the queue that a packet. So the NQ queue depth is when the packet gets in queued, records how deep the queue it's in is in units of cells, not in bytes, but cells are in Tofino 180 bytes long. So we can pretty much figure how many bytes it is pretty closely. And then the DQ queue depth is in the same units of cells, but it's how many, what the depth of the queue was at the time the packet was DQ'd, just before it goes to the egress parser.
And I would say that's my favorite intrinsic metadata too. As someone who was born in the Soviet Union, I can totally relate to these two fields, because you would come to the store and see a long line. And so it's really nice to know how many people were in line in front of you. And then you finally get through that line, exit the store, and satisfyingly see the line, which is even longer. And probably those people won't even get the stuff that you bought.
All right. I hope I never have to experience that, but interesting stories, definitely. Another thing I think I mentioned before is the timestamps here. We have the global timestamp when the packet reaches this one. This was into the parser, right? Or out of the parser? Do you remember?
That one is when the packet gets into the egress parser.
Okay, and so this is the one that I mentioned earlier. We can use the difference between this value and one of the two previous ingress timestamps if we want a good approximation of the queuing latency of this packet.
And also, speaking of the precise timestamps, by the way, we have some others that we can capture at the very end after all the egress processing. So we can use them to implement either one-step or two-step 5888 protocol. So continuing my Soviet Russia jokes, that would be the same as KGB officers logging the time when I finally got home with the stuff that I bought while waiting in that long line.
I'm just impressed that, yeah, so for one, measuring your length in line in nanoseconds, that would be a pretty big number, I imagine.
Oh, yeah. But remember that with 48 bits precision, these nanosecond timestamps, they expire in about 3¼ days, and I've never stood in line for such a long time, even in the Soviet Union, so that's okay.
And hopefully no packets will ever be in Tofino that long. Nowhere near. So, as we've all seen for other architectures, as well as for the TNA architecture, we need to define not only which blocks are P4 programmable and which ones are fixed functions, and all the intrinsic metadata. There's also the library of externs that the architecture provides. So what do we have in TNA for there?
Well, TNA offers a rich set of externs. Some of them, such counters and meters and registers, are definitely quite similar to their V1 model or PSA counterparts. There are some useful extensions nevertheless, but generally they're quite similar. So what I thought I'll talk about is a couple of cool externs which are Tofino specific. The first one is hash.
That's not new in TNA, come on.
Well, it is true that hash is present in both V1 model and PSA, but in case of Tofino, hash can work with another extern called CRC polynomial, and that allows the user to specify an arbitrary polynomial to calculate the CRC. More importantly is that when we instantiate that, and here I'm showing how to do that, you first instantiate the CRC polynomial extern, and then you use it to create a specific hash extern. Once you instantiate anything in P4 and give it a name, you have the opportunity to have an API to control that object at runtime. And that's precisely what we can do. So there are two things that TNA allows us to do. First of all, we can control this poly object and specify the coefficient, the polynomial, and the other parameters at runtime. So we can transform it from CRC32 to CRC32 Castagnoli as here, or to any other CRC32 that people would like. That's number one. And the other thing that we can do is we can control the hash extern itself. And specifically what we can do with it, we can decide which fields from the ones that are mentioned inside the get method will be used to calculate the CRC. In fact, we can mask some portions of these fields, and we also specify that two fields are symmetric.
Right. So yeah, when you want to make fields symmetric, for example, there's often cases where people want the same hash value to be calculated for traffic, let's say from host A to host B, or from host B to host A, where the source and destination address are swapped and the source and destination L4 ports are swapped. So we want, in hardware here, we have the capability to swap them just before calculating the hash so that we get a consistent, we sort them basically, and then get a consistent hash in each direction.
That's right. Obviously, there are lots of details to that. So if you'd like to find out more, you're welcome to attend our academic classes. But in general, the hardware that we have is pretty simple, but at the same time, pretty capable as well. It is essentially a linear code generation matrix. And so all these manipulations we just described, and that might look very complicated, in fact, are very, very easy to implement.
But the next extern is even cooler, right?
Yeah, I think the other extern I'm recently very excited about is a very unusual capability that allows me to even remember some of the math classes I took many, many, many years ago. So what Tofino has is a special extern called low pass filter, or LPF, and it allows people to calculate exponentially weighted mean average.
So this is good for smoothing out various kinds of bursty data sources, right?
That's right. And in fact, it has a couple of different modes. So first, you can feed it the values that represent, say, queue occupancy from the egress intrinsic metadata, which is discussed. And as a result, you'll get a nicely smooth value that actually shows much better trends in queue occupancy, let us put that way, so they're not affected by the instantaneous fluctuations. Or you can feed it, for example, packet lengths from every incoming packet that we were receiving. And as a result, this extern can calculate the average data rate for these packets. And it will be done automatically. It will take into account their arrival times. And so just based on this packet lengths, we can have the very accurate packet rate calculations as well.
So that sounds a lot like an integrator.
That's correct. So if for those people who might still remember their basic electronic classes, LPF essentially simulates a simple RC circuit. And we know that this simple RC circuit can be used both as a low pass filter and as an integrator. It depends on the ratio between the time constant and the rate of the data change. So here, obviously, we don't use the analog circuits. We do it digitally, but the math is still the same.
Yeah, DSP-like. Can you build a multipole filter out of this too?
Actually, yes, we can do that. That's precisely what I have here. So we can filter an input value and then use the output of that as the input to another filter and so on. And this is very, very important to remember about Tofino. No matter how cool the resource is, we have them in each and every match action units. They are exactly the same. So we can repeat this cool operation as many times as we want. The other thing I wanted to point out, of course, is that these externs, they also have their own APIs, and following the standard methodology that we have, they also look like tables. So very, very easy to control and manage.
So while I would be a kind of network geek and just think about only using this to analyze things like queue depths and times and latencies, you've got another example though, right?
We can actually use Tofino to do stock price analysis. So here I plotted some of the prices from Intel stock prices from some time ago, and I calculated the exponentially weighted mean average using the standard formulas, and that is our red line on this slide. And then what I have done, I used Tofino to calculate the same thing using the LPF extern, and this is represented by the line of the green color. And you see that, except for the very beginning, these lines are pretty much the same. So close they are, so our calculations are very, very accurate. And then, of course, I used another low-pass filter with slightly different parameters, where I used a lot more smoothing to smooth out all those minute fluctuations in the stock price.
Just a minute, I have to go make a trade. Oh, wait, no, sorry. I'll do that later. But past performance is no indicator of future returns. So talk to your qualified advisor.
I know you also have a favorite Tofino capability. So why don't you tell our viewers about it?
I really like the packet generators. I think I just can't imagine doing without them. So, I mean, certainly Tofino is good at, we think of it as always processing packets. And the way I like to think about packet generators is it lets you turn events that aren't originally packets into packets. And then, of course, you can write P4 code to process those events.
That's right. I think as a bit of trivia, it might come up as a surprise to our viewers, but one thing that you cannot write in P4 is a hello world program, because this program traditionally requires no input, and P4 programs really cannot operate without a packet which serves as an input to the program. So packet generators kind of solve this problem and they allow us to generate packets at will without waiting for the network to deliver any packets into the device. So let's tell our viewers how they work.
So there's one packet generator hardware block for each of the 4 pipes. And whenever the packet generator injects a packet into the parser, it will always appear, its ingress port intrinsic metadata field will always be 68, which we can use to distinguish these packets from others. Every packet generator hardware has inside of it configuration for 8 independent generators, which we call apps.
And so that allows us to implement multiple different functionality at the same time, right?
Right, multiple different triggers for could be completely different reasons, or we can combine multiple of these related to one feature, depending upon what you want to use them for. So one of the things we need to configure in each of these 8 applications is the trigger, which we'll talk about later. But also, once a package is generated, there'll be a hardware-specific header that's created, but also the payload that's created that's appended to that header. And each one of these packet generator hardwares has a 16 kilobyte packet buffer. And for each of the applications, we specify its own starting offset within that 16 kilobyte packet buffer and a length. And then that buffer will be read and that data appended after the header.
And then there are also triggers, of course, that you mentioned, right?
Sure. Yep. And so we have 4 different kinds of triggers implemented in Tofino. Let's go through them. Each application can independently configure its own trigger independently of the other 8 applications. So we have 2 kinds of timer triggers. One is a periodic trigger where we specify a period So for example, we could say every microsecond, I want this periodic timer to trigger, and it will generate one or more packets we'll talk about later. And then there's also the one-shot timer, where when you the control plane arms this, it will specify how far in the future it wants the trigger to occur. Another very useful one, if you want your fast reroute capabilities especially, is the port down trigger. So in this case, all the ports within this pipe where the packet generator hardware block is will be monitored by the packet generator hardware. And if any one of them changes from an up state to a down state after the control plane has armed it, then that will cause this application to be triggered and to generate packets. And then another one is the ports on which the packet generator hardware exists are also configured in loopback mode. So you can send a packet out of that port, it will get looped back and pass through the packet generator and back into the ingress pipe. And while they're streaming through the packet generator hardware, it's watching the first 4 bytes of each of these recirculated packets. And you can configure an application with a 4-byte value and a mask. And if those first 4 bytes are recirculated match that value and mask, that will trigger the packet generator as well.
And of course, there are APIs that allow the control plane to configure all these different features in those packet generators.
Exactly. Each of the 8 applications, yeah, we get a choice independently of the 4 triggers, the payload, etc.
So how many packets can the engine generate?
So I've been talking now only about the word trigger. And so every time this trigger occurs, the periodic or the one-shot timer, we can configure a lot of packets up to, we configure a number of batches that we want to generate. Is one number that we configure, and then within each batch, how many packets we want to generate within that batch. And then you also have configuration options for how long the time is between the start of 2 consecutive batches. You can either specify that as a constant number with a jitter of 0, or you can specify as a constant number plus or minus some pseudo-randomly generated jitter in that time. That's the inter-batch time. And then there's similarly within a batch, we can have a constant or variable inter-packet time for packets generated within the batch.
Wow.
And so, yeah, we have up to 64K of batches, up to 64 packets per batch, gives us a total of
4 billion packets sounds to me.
That'll take a whole second.
Yeah, that will take a while to generate. I guess we can use Tofino to build some really nasty devices that can produce serious denial of service attacks.
We certainly could. So you may have to get a license before you can buy Tofino. I don't know. No, we don't. You just have to pay for them.
Well, I guess there may be some more constructive applications for this feature as well. And one of them would be to use periodic timer triggers to implement BFD or similar protocols.
Yep, I'm working on an application right now where we want to use the periodic timers to help us implement little countdown timers inside of P4 register arrays so we can retransmit timeouts on streams, reliable streams.
Right, so here we basically program the device, create the payload buffer, set the periodic timer, say to 500 milliseconds, but it could be much shorter. It actually has a nanosecond precision. And then once we start it, the packet generators will generate these packets as quickly as we want without any other CPU involvement. So a very powerful feature.
Definitely. Yeah, no, and one impressive thing to realize is with 1.2 billion packets per second per pipe, you can have a packet generator that generates 1.2 million packets per second in a pipe, and that's 0.1% of your packet processing capability in a pipe.
Yeah, essentially 100 gig per pipe. That's what we can generate effectively. So by the way, if we want to do that, we also, going back to my nasty idea about denial service attack, these packets go through the standard processing. So even though the packet generator can generate 1 packet, we can always multiply them in packet replication engine to achieve much higher bandwidth.
And as mentioned earlier, there's a special header that Tofino sticks in front of the packet generator sticks in front of each of these packets. And so if you're generating from a single trigger multiple packets, part of that header is typically the which batch number that the packet is in and which packet within that batch, so that you can even generate many packets and say use that packet ID or batch ID as an index into a table or some P4 register ready to do something a little bit different with each packet.
Okay, well, the other cool feature is being able to generate packets when the link goes down, right?
Definitely. Yep. So if you, this is good for fast reroute and or, quick notification of either your local control CPU, although it has other ways of learning of links going down, but also neighboring switches. You can inform them with packets that one of your ports has gone down.
So all you need is to basically program the app in the packet generator and then wait. And for example, here we can also ask to generate multiple packets. That's possible. And then we can wait for someone maybe to cut the link, and immediately after that, we'll see the packets going out to notify maybe our peers in the network or to do something else. And this all is done at data plane speeds and without any CPU involvement. So fast rerouting can be very, very fast indeed.
Don't you get in trouble when you walk into a data center with scissors?
Well, we can simply unplug the cable, I guess. It was more difficult to draw.
Yep. So, Vlad, what kind of software do we provide to control all these features?
Well, this software is called Intel P4 Studio SDE, which stands for Software Development Environment, and it is comprised of several components. At the very bottom, obviously, if we want to use the real ASIC, we need to have a kernel module, and we provide a choice of two so that we can communicate with the ASIC. And the rest is done in the user space driver, which in turn consists of multiple layers. At the very bottom, we have a thin layer which provides the rest of the code with routines that we need to abstract the operating system services from. So things like memory allocation, thread management, timers, etc. And we also have a set of open source libraries that we rely upon to implement efficient data structures. And on top of this thin layers, we have a low-level driver that knows how to access the device registers, perform DMA, handle interrupts, do things like that. And then on top of this low-level driver, we have two major components. The pipe manager, which manages all P4 programmable portions of the device. And we also have fixed function APIs, which manage, obviously, fixed function configurable components, which are not programmable in P4. That means ports, traffic manager, packet replication engine, and so on and so forth. Also, when we work with the real ASIC, we need one extra component, which comes from the board designers or ODMs, and that is the board support package. Still, these are low-level layers. They're not supposed to be used by the NOS designs directly. Instead, what people do, they use the API called Bfrt runtime interface to communicate with the device and therefore communicate with the data plane program which is running on it.
So this sounds like a lot of moving parts to keep track of.
Well, that's true, but that's the real hardware. Of course, when you have a model, especially behavioral models such as BMV2, you would not need a port support package to deal with the details of physical ports. Also, BMV2 is a very high-level software, so basically the driver is built into it. When you load the JSON of the compiled P4 program, the behavioral model knows exactly the names of the tables and what to do with them. Whereas Tofino is a pure hardware target. It, in fact, doesn't know anything about P4. So the driver needs to be aware of very complicated mapping that exists between the P4 program and the real hardware. And
so how does the driver learn about these mappings?
Well, it all starts with the P4 program anyways, which we hopefully write to support our control plane program. We compile it using a Tofino compiler, which is called P416. And this compiler outputs several important files. One of them is the binary code that has to be loaded on the ASIC. And the other one describes all the P4 objects defined in the program. That's the file Bfrt JSON. And the third file, context.json, is precisely the file that describes the mapping from one to another. So once the driver process has a chance to read those files, that's precisely when it becomes aware of the mapping, and the APIs become capable of programming exactly the tables and other objects that are defined in the P4 program. Last but not least, what we also do, we provide a nice Python-based CLI that can be used to manipulate the configuration of all the P4 objects. It can be accessed directly or through a TCP port, so that designers can quickly prototype things or debug them if necessary.
So that covers all the P4 objects that we have written in our program. What about the traffic manager and Ethernet ports?
Well, actually, it covers everything, because the basic idea behind Barefoot Runtime Interface is that the configuration of any object can be expressed as a table or table-like object. So in reality, Barefoot Runtime Interface, or BFRT API, that's how we call the locally callable portion of it, covers both P4 programmable and not P4 programmable components. It really doesn't matter. They all look more or less the same, just as tables.
And this is all in one process here, the control plane app you've shown.
Yeah, that's true. This is a traditional deployment model that is used by majority of the people who design NOSes. Everything is done within the same address space of the process, because it is the most efficient way to get things done. But certainly there are other arrangements as well.
So yeah, the P4 Runtime API has been defined as a remote API, and Intel provides one of those as well, right?
Yes. Barefoot Runtime Interface has a very similar component called, surprisingly, BF Runtime, which is based on the same underlying technology as P4 Runtime. So BF Runtime server sits on top of our locally callable BFRT APIs and uses protobuf or protobuf library, I guess, to serialize arbitrarily complex messages, and gRPC to be able to send and receive those messages and communicate with the clients. And because of that, the clients can be run as completely separate processes, or can also be run on a separate machine if desired. So the rest works pretty much the same. So we can compile our program, obtain the same artifacts, load them inside our driver process, and then the client, which communicates with our driver process, can download the description of the P4 objects that exist in the given program and start communicating and programming the device separately.
So I noticed in this slide, the device isn't the ASIC though.
That's true. Besides the ASICs, of course, we also provide the register accurate Tofino model that can be used in place of the real device for most types of development. And because the model is register accurate, it works exactly the same with the same drivers and executes exactly the same compiled binary without the need for any modifications. I'll tell you, in course of my work, I probably spend 90–95% of time working with the model and not with the real device, because it's so much easier. Same thing goes about training. We use the model to a great success.
So in this scenario you described, you loaded the binary from the locally running software, but the P4 Runtime API, I know, provides the ability for the controller to choose the P4 program and load it, right?
Yes, and because gRPC is a very generic communication channel, it's not that difficult to do exact same thing with Barefoot runtime interface, and we do support that. In this case, what will happen is the files that are generated as a result of program compilation needs to be read inside the controller first. And then the controller can use the same gRPC channel to push those files to the agent or agents. And the last thing is probably the most important. If you say have a data center and you have maybe hundreds or thousands of systems, you can first push the same program to them and then start to communicate with them. So this is all supported.
So what kind of differences would you say there exist between the P4 runtime API and the Barefoot runtime API?
Well, first, I will start with the similarities because both APIs are actually program-independent APIs. And as a result, they only need a few generic functions to manipulate the objects that are defined in the P4 program. So their interfaces are data-driven. And in a sense, when we look at standard match action tables, both APIs look at them pretty much the same way. You have an entry which contains a key, contains the action, and then a unit of variety of action data. The key itself depends on the match kind that is defined in the program. And then, of course, the action data depends on the action that is specifically defined. So this is pretty much the same idea. In terms of differences, the main difference is that the Barefoot runtime interface was designed to control any kind of object, be it defined in a P4 program or not, by exposing all kinds of objects as stable. It could be externs, for example, direct externs can be thought of as extensions of existing tables. Like here I have direct counters and direct meters. We can think about indirect externs also represented as tables where the index of that indirect extern is the key. And what is really important is that Barefoot runtime interface allows us to control fixed function components using exact same technology. It is possible to do with P4 runtime as well, don't get me wrong, but it's because P4 runtime allows people to define vendor-specific objects, but their nature is not mandated by the specification, so they can look like anything. Whereas in Barefoot runtime interface, we basically impose, like I would say, a self-discipline where we require that all the objects, no matter fixed function or P4 programmable, they all look like a table. So once you have mastered the techniques and you know how to operate with the tables, you can operate and control any object defined in your program, no matter if it's some standard extern or a custom extern or a fixed function component in some custom device. The other important difference that we briefly touched upon is that we have two explicitly defined interfaces. One is locally callable interface. We support both C and C++. And of course, this interface provides the most efficient access to the device. And then separately, we have defined the remotely callable interface, which allows us to pass gRPC messages. That's very important because these interfaces, generally speaking, are different, not quite interreplaceable. And so it is important to define both, and then people can use whichever they like.
So I think I'd love to see an example of how people develop programs with these tools day to day.
Sure. Absolutely, Andy. So let me show you my VM.
I recognize that wallpaper. Where are you running this?
Well, this is actually being run on Amazon Web Services, so in the cloud, and that's precisely the type of VMs that we use when I teach Intel Connectivity Academy. It gives us a lot of advantages because obviously Amazon has data centers all across the world, and I can instantiate as many VMs as needed for each of the students in all different countries. Sometimes I start instantiating them in Japan and go all around the globe, ending up in California or Oregon. Up to probably 7 or 8 data centers that can be running those VMs during Intel Connectivity Academy sessions.
The sun never sets on AWS nor on the Academy sessions.
Exactly. So here I just started a simple window. If we look inside, I have some programs that we have for the labs. And then if we look at the home directory, there is a version of SDE that I've already pre-built, of course. I've already selected that I'm going to work with this SDE. And if I would like to compile a program, it's actually done very easily. So all I need to do is to call a script that will compile the program, basically like any other compiler. You can call compiler directly as well, but for the simplicity's sake, it's better to install the programs or the program artifacts in the right location. So that's why we use a little bit of scripting. So let's compile a simple program.
And so the script only needs just the program name as an argument?
Yes, in fact, it's a pretty universal script, so it even detects the language the program was written for, and it detects the architecture. So if, for example, I write the program for Tofino 2, then it will compile the program for Tofino 2, and so on and so forth. And so very quickly, you can see that the program got compiled and installed. And so then it's just time to exercise this program. So I already prepared a couple of other windows.
So we probably need to run a copy of the model on this machine.
Yes, absolutely. So here will be my model window, and I typically try to use different colors just so that people see what's going on here. So to run the model, I've already configured my virtual Ethernet interfaces. So I will go inside the SD directory and say run Tofino model and specify the name of the program, which was simple L3. And so the model will start. This little delay is an AWS artifact, and that happens only the first time you start the model, so don't worry. And then I will go into the other window and run our user space driver process, which is called switchd. So run switchd, and also specify the name of my program, simple L3. And so we can see that the driver took hold of the model and basically reset the switch, essentially. And it's initializing in that, and very soon it will be ready to process my commands. We have a prompt here. I can use that prompt, or I can do it from a separate terminal. That's quite useful, especially if I would like to run the driver in the background in the first place, or if I would like to access it remotely. So I can start the command line interface. It has many different sections, as you could see, but the most interesting one is called Bfrt Python, which is the Python interface to the program. So this is a full IPython interpreter. And in there, I have a hierarchy of objects. So I can start with a root object called Bfrt. Underneath, there is an object which represents my whole program, simple L3. And if you remember, when we created the switch package, we created that out of the package called pipe. So inside there is such a package. And in there, we can see the names. So for example, of my ingress and ingress parser, that's the only two components because this is a very simple program. that's the only places where I do have some controllable components. And for example, I can go here inside the ingress control and see that it has two tables, IPv4 host and IPv4 LPM. So we can, for example, add entries to these tables if we'd like. Now we can dump them and we can do other things. So I can say IPv4 host, and each table has a bunch of methods. We can see them here. So for example, one of the methods that is really interesting is called info. So that shows us what's in the table, the full name and the capacity and which fields are used for match and what kind of actions are in the table and so on. So if we want to add an entry, we can do it in a variety of ways. So let's go inside this table, IPv4 host. It has a couple of methods. So you can say add with a drop action or add with send action. If we do that, you can also get some help, and it shows you that if you want to add an entry with a send action, you need to specify the destination address. Obviously, that's the key, and the port, and we can see the types of these parameters. So there's tons of online help, which is automatically generated for these functions. So here we can do it. And of course, we can do it, for example, for the address 192.168.1.1 and send the packets to port 1.
And you always think in hex, right?
Well, yes. If that's too cryptic, remember this is Python, so we can always say, for example, from the module IP address, import the function called IP address. And then we can say IPv4 host, add with maybe send function again. And we can say IP address. .192.168.1.2, and then send it to port number 2.
So this is the Python bindings for the control plane APIs, and the C++ looks quite different without the interactive interface, but this is great for playing around interactively.
Yes, this is a much easier interface to learn because A, it's Python, and B, it's done in such a way where you can do lots of things very, very quickly. Obviously, we can dump this table. By the way, right now, if I say dump, I'm in the ingress control, so it will dump all the tables which are inside. But in this case, I probably will, well, I'll dump my own table. So IPv4 host. Again, we can see different methods that we have on this table, and we can say dump. And so here we see the dump of these two entries. We can also say dump table equals 1 or table equals true, and it will print it in slightly more cohesive way. And so now we have our tables configured, and what we can do is we can maybe open another window and run Scapy in there. I'll just move it a little bit. And so let's say sudo Scapy.
Favorite way to construct and deconstruct packets.
Absolutely. So we can simply say send packet, and let's make it a very simple Ethernet packet followed with the IP header with the destination address 192.168.1.1 and maybe some payload for workshop, as easy as it can get, and send it into some interface. This will be port 0, represented as v1.
Yeah, there's a v to port mapping like there is in BMB2 here for the model here as well.
The default that we use is pretty much the same as BMB2, or maybe, well, it's difficult to now see who was first, who is the second.
But there's a README file with the default mapping that's good to refer to.
You can always specify a custom mapping file if you'd like to. And so I just send the packet, and we can see that the model produced some output. If we scroll a little bit, we'll see the model log, and it is pretty instructive. So we can see the packet ingressing. It was a minimal size 64-byte packet, which later on got parsed, and we can see exactly how parsing was done and which parts of the packets were extracted. So some of the things that you previously mentioned, the packet came in as 64 bytes, but then the architecture, the inner logic of Tofino prepended 16 bytes to that packet, which contain some of the interesting information, like, for example, the timestamp. And then only the packet starts. So the packet gets parsed, and then it goes into our processing. We can see the outputs, like, for example, the if statement that was executed to check if that was an IPv4 packet. And then, of course, we had a hit in table IPv4 host. We can see the key with which the table was hit. And subsequently, we see the unique category port being set to 1. And at the very end, after all the processing, and you can see that the model shows that there are other stages. We just don't do anything inside them. Finally, the packet reemerges in the egress pipeline, and at the very end, we can see that it has been transmitted without any changes to port 1. So this is a very simple way to work with our programs. Obviously, we support other things. For example, one can run tests on these programs, the standard PTF tests. We use the same infrastructure for testing. What I thought would be most interesting to see is a very special tool that we provide called P416. So what P416 is really a tool which allows us to see what did the compiler do to a program. You can load a program into that tool. I have plenty of programs that I've compiled on this system. We can start with that simple program that we have just ran, but there could be others. And so you can see how many stages the program occupies. We can see, for example, how different tables were placed inside match action units, how the parser was generated. So, for example, here we can see Parser Graph. This one is obviously very simple, but if you talk about some complex programs like a real data plane program, then things start getting a lot bigger and a lot more interesting. Like, for example, parse graphs could be pretty complex. And then, of course, if you look at the layout of the program, you can see it being laid out across all 12 stages with different tables occupying various spaces inside the SRAMs and the TCAMs. You can see, for example, the programmable header and metadata bus, which we know is called PHV, how this one is being allocated and used across many different stages. So this is a great tool to do both fitting of the programs when you need to make sure the program fits into the available resources, as well as when you need to debug certain difficult cases. That's an available tool that we provide. There's some other interesting things. For example, you can see the analysis of the power, and you can see which tables consume more power or less power. So you can even optimize the program for the power consumption. And I think another important observation here is that if you think about a fixed function device, because you can change what the tables are doing, if the table is not used, it kind of wastes power. So here you can see exactly what you're using the resources for.
So it's like a power profiler, just like when you're performance profiling, you should focus on the things taking most of the time. When you're power optimizing, you should focus on the things that take the most power.
Absolutely. So here we can see the tables which use more power. You can also see the latency analysis for the processing inside the ingress or egress and so on and so forth. So lots of interesting insights that we can glean. And by the way, I also think this is a great educational tool. So if I need to explain to the people how the device works, what are different components inside match action units, then definitely this is something that I use a lot because it shows everything visually. It's very easy to explain. And if anyone decides to join us at Intel Connectivity Academy, we'll learn a lot of things about Tofino.
Yeah, no, I know from this demo and from the Academy class that it's not obvious what all these charts mean at first glance, but it certainly helps to have the training to dig into the details here.
Absolutely. This actually brings me to my shameless plug, where I wanted to talk about Intel Connectivity Academy, because as Andy can attest, this is a really great course where I provide comprehensive training for both beginners and experts. Today, obviously, we have to deal with online Zoom sessions, but they are live. They're not pre-recorded, so there's an opportunity to ask all kinds of questions. And generally, it's a lot easier to be in a live session than just watching a very long recording, no matter how interesting. And what is really important is that these classes have online hands-on labs, which are run on the same VMs that I just demonstrated. And so specifically for the P4 workshop attendees, there's a special coupon code, and we'll provide the links down in the description of this video. So for the next classes that we are about to schedule, or the ones that are already scheduled, you can use this coupon code to receive a discount. I will just make one caveat that you have to be an Intel customer, so you have to have all the paperwork signed, but otherwise would like to invite you to these training classes.
Yep, and I can attest that as you might expect, the 90% of the value is in that live Q&A.
And with that, I think we would like to thank everyone for being with us to listen to our chat. Hopefully you learned some interesting things about Tofino. We are really excited that you are here and you're watching us. You're interested in P4 and data plane development, and we hope to see you in the future workshops or future trainings.
And hope you do cool stuff with Tofino.
Yep. Cool. Thanks very much.
Thanks.
Thanks, Andy.